Thank you. So, again, welcome to my session for the ACCU 2021 virtual conference. Sessions, hang on, make sure user interface is just fooling me here. But, yes, Frictionless Allocators. I'm Alisdair Meredith, a senior developer with Bloomberg, working with the BDE team. And joining me on this session to answer Q&A live while I'm talking in the Q&A feature of Zoom, colleague Joshua Byrne, who also knows this material fairly well. So if I'm rambling on and leaving people behind, please do feel free to ask your Q&A during the session. But Joshua is going to answer those with the text facility. I'm going to keep talking. So a quick outline of the talk. It's going to go through fairly fast paced at the start because I've got a little bit of recap material, which is intended to be a revision for how allocators work in C++ today. If that leaves you behind because I'm going too fast, this is intended to be a revision, not learning material, but it will not matter too much if you don't absorb all that, because we're going to be talking about what we want to actually deliver in the latter half of the talk anyway, and hopefully that will be enough to catch up. This is just setting the groundwork. So I'm going to start with the basic idea of what do I think an allocator is. It's basically a service that's going to grant use of memory to clients, because pretty much all software needs to have memory to contain code and data that's executing. And nice clients will even return that memory back to the allocator. But, you know, look, I'm already fooling myself as I'm going. We have certain use cases where even that might not be necessary if the allocator itself can effectively garbage collect and pull the whole region back away later on. So, why do we want allocators as a specific feature in C++? Is the new operator itself not good enough? And the basic answer is performance, performance, performance. This is why people mostly want allocators. And then there's a couple of extra uses that once we've got allocators that can be helpful for instrumentation, telemetry, and special memory uses. So what do I mean by performance? Well, we've got a couple of previous presentations that have been given on that you can see online now. We've got John Laker's talk here, a couple of papers. We'll go through fast, but that will be there for people to catch up on when they're reviewing the talk afterwards. Looking at the slides. But the key thing we found is we were doing our benchmarking of basically artificial benchmarks for how allocators could work in practice. We saw a factor of 3 to 5 speed up with careful use of allocators in specific scenarios. So there's a real gain there to be found. So how do you get benefits out of allocators? Well, the obvious start is you want a faster allocator. So the general purpose, new, people are always optimizing, trying to get a better version of operator new that will generally reduce contention and synchronization, as it's a global service for all your threads running in your application. But if you start taking control and providing your own allocators, you can avoid the need for synchronization at all if you know that all memory used by a single thread will be not shared between threads, and that allows you to have an optimized allocator in those cases. And another scenario we have is simplified bookkeeping, where you simply allocate, say I've got a big slab of memory, and when it's gone, and anything that wants memory can simply advance a pointer through that, never reclaim the memory. It's a really fast allocation strategy that certainly doesn't suit every need, but when it helps, when it's useful, it's a faster allocation strategy. But in practice, cost of the allocation is not where the performance gains are to be found. The key reason we want to take control of allocation is to keep memory local and together so that related use of memory is usually happening sequentially. So you want to make sure that the related data with your application stays located in as few cache pages as close together as possible. L1, L2 cache is obviously the ideal, and if you keep hitting your data pages, the CPU is going to do a good job of trying to keep data in those. By use of memory pooling, you can provide a better way of controlling, managing your own data to give the CPU the best chance to handle that and make sure that your data isn't scattered across different data pages throughout the application. And this has two effects. We call one diffusion, which is the effect of memory slowly scattering through memory, meaning that you've got to page in more and more pages to collect that data, but then that has a performance impact. The other use some people might be more familiar with is fragmentation, where because memory is now scattered around, going to the global pool to say, give me some more memory gets increasingly difficult as the free slices of memory start getting smaller and smaller, and in the long-running application, you might have a large amount of memory that's free, but not in sufficient size to actually fulfill allocations going forward. So that's a large part of where performance comes from trying to manage and keep your data for your data structures close together so that the access patterns work well with modern computer architecture. That's the goal. We have two common strategies we use with our allocators to achieve this performance. If we can allocate off the thread stack because it's a short-lived object that's not going to pass memory outside that function call, we can try and allocate the actual memory on its stack itself, and that's close packing to your regular data uses you're going to get to have really efficient cache use. And doing that, we might have separately managed a pool for our data ourselves, which admittedly, if you look at operator new, that is effectively a pooling allocator. That's how these strategies work in general. But if you know which of your data structures are going to work separately, you can give each its own specific pool so that all the data for that data structure is managed in separate pools, and that helps keep the locality and keeps the performance live. So that's a large part of the goal in the performance. As I said, we've got other utility features that we can have with telemetry that are helpful when debugging, profiling, logging to have some clue what your system might be doing live, and naturally test drivers just to make sure that the memory usage patterns are the usage patterns you're expecting. It's not just memory leaks, but making sure, as you say, if you're trying to have data in different pools, you want to make sure that the data structures are each using the correct pools. So testing allocators is, again, very helpful there. Another aspect people want to control with allocators is some kind of special memory. Two common cases are something like inter-process memory, where you use memory mapping and you're now sharing handles to memory that might map to different locations in address spaces in different processes, but it's effectively the same memory that they are all sharing. And again, with video memory on lots of GPU type at the software, perhaps different channels and ways that you want to specify access to memory in these other special hardware regions. And handling special memory often means using some proxy rather than a direct raw pointer to describe that region of memory. Needs a little bit more information for the system to work with it. And again, that won't come out of operator new, but once you provide your own special allocators, that is something that you can address. And just to mention there, so we spoke about the performance measurements we had with our benchmarks on the that we published a few years ago. In order to make sure that what we're saying isn't just Bloomberg saying, yes, we ran these benchmarks, you can go off and run these artificial code that we tested and demonstrated the system works. We're working with Emery Berger, who is a professor at University of Massachusetts. He developed the Horde memory allocator that's effectively a plug-in replacement for new. And he's working with us to give a more realistic benchmarking to demonstrate how does our use of allocators really reflect real-world usage. So he's setting out to demonstrate the value of custom allocators, and then by instrumenting with his testing methodology, develop tools that can help dial in to say, these are the places in your program that will really benefit from custom use of allocators. So, early start, what we're doing, we're working with some of the Bloomberg BE style allocators to try to get some more real-world examples rather than the specific examples we did on the benchmarks, let's say, after a few years ago. So we've got a couple of benchmarks here. Stress test is, again, an artificial using the Bloomberg data types to compose a large sort and filter, so working over a large data structure, but artificially just to try to stress the system. Then we've got something called Moda, which is modeling some of the actual real-world application pipelines that we use within the Bloomberg software to say, this is actually a real-world application that is pulled and modeled on actual real-world data in a real-world application. So reflecting actual use rather than pure benchmarking. And the early results, again, we've got a long way to go before we've got something that's final, but the blue on these charts is what happens if we've shimmed in rather than the Bloomberg allocators. We're trying to shim in. What happens if those went to just back to using operator new for all the different calls? The red is, and then if we shim out the regular system allocator with Emery's Horde allocator, we can see there's an improvement there. The yellow bars are then say, okay, this is what you get transforming the blue to the yellow just by plugging in our original use of optimized allocators for this application. And we can see flagging up here, Emery's quite a 25% speed gain. Note that 100% speed gain would mean you take no time, so it's not a multiple, it's how much has come out. If it ran twice as fast, you'd be on the 50% line. And finally, of course, you've got what happens if you combine the Bloomberg allocator and the Horde, which gets you the green. So certainly we expect to hopefully see some benefit from Emery's improved new, but the majority of the benefit, and that seems to be what we see here, comes from our use of the allocator strategies that we deploy at Bloomberg. So that's my motivation for how we get here. Next, I want to take a quick review of how allocators work in C++ today, which is C++20. So again, this is a hasty revision if this material is not intimately familiar with you. It's a rapid fire scale through how allocators work. The key change that happened in 2011 was rather than directly using your allocator in the standard containers, we suggest beyond, you gain your access to the allocator services through the Allocator Traits type. This means that the Allocator Traits can supply any missing functionality so that allocators are real simple to implement and containers can get anything they need by anything that says see below says if you do not provide this type in your allocator, the traits know how to synthesize an appropriate type to use in that case. So anything that says see below, that's the allocator trait. It's just going to provide services for you when the default, when you want to fall back on the default. Likewise, how do you request memory and construct objects? We've got a system of static member functions, where you pass the allocator that you wish to be using through to say, use this allocator to allocate me some memory, to construct or destroy elements. And one of the things you'll notice here is there's two different notions of pointer. The blue pointer says I have a pointer type def that says this is the kind of pointer that my allocator works with. This is how you can support those special allocators that handle things like shared system memory or video memory and so forth. Whereas when you want to construct and destroy elements in your container, they might need to know about your allocator as well. So that's why we go through the interface still to construct and destroy elements, and those need the real address in memory, the T star of your object, not the actual pointer, not the special pointer type. But the other convenience we have with construct and destroy, because these are the kind of things that you're going to be using quite often, and containers, you pass them one kind of allocator type, but if you've got a list container, it's going to be storing and allocating memory in a node, not in the type of the element. And to avoid having to go through rebinding and doing lots of clever programming work to hook those up all the time, the construct and destroy methods are templates just so that you don't need to have different allocator instances to allocate your node to construct your elements when they're all different types. And finally, we hit these things called propagation traits, which I'm going to talk a little bit more about later. But so just go back. But these deal with if I'm copying or moving a container or something that uses memory, does the allocator move with the type, or does each type maintain its own allocator that is set the construction time, and then that is the policy for that object for the lifetime of the program? This is your control over that. In C++17, we added a few new facilities. We have the is always equal trait, because it turns out that when you want to check if two allocators are compatible, we use the equality operator for that. And for common cases where an allocator is stateless, like the standard allocator, it's just always going to be true. It's not a runtime query in that sense. You know the result. And having the ability to inspect that as a type trait is really handy for trying to set no except specifications and guarantees to deal with it with exception handling. So that was factored out into an extra trait. And in C++20, the big deal we get in 20 is that all of our allocate methods are now const expert. So we have the notion of being able to do compile time allocation, which sounds wonderful until you realize that you can't actually have compile time allocated objects that last the duration, const expert objects that last the duration of the program. This is merely for creating objects during evaluation of a const expert function that will be cleaned up by the end of the evaluation of that function. They cannot escape a function evaluation in that sense. But we're still working on that for 23. So even the idea of compile time allocation is working its way through C++. The other facility we added in 17, which is key to this talk, is the notion of polymorphic memory resources. This is the Bloomberg model of saying, I want to provide the allocator to my container, my data structure, at runtime, not determined up front at compile time, so that different containers can have different allocators. Specifically, if I've got 2 or 3 maps, they will each want their own pool. They will not want to be sharing the same pool in order to keep the locality of the data in those different structures optimal. They each have their own pool. The notion of this is we use a base class, memory resource, that has a classic C++ virtual table-based interface. We can see we're using what's called the non-public virtual pattern, where the virtual functions that implement the facility are all protected, although the destructor, of course, remains public and virtual polymorphic type. We then access that functionality through these non-virtual functions. So these are not overridable. These just dispatch the calls down to the virtual functions. Why do we do that? Well, we've got this extra alignment property. In addition to the size of bytes you're asking, though most often people just want to allocate bytes. So these are going to default. And having default arguments and virtual functions gets a bit messy. The allocate and deallocate function will just dispatch down and make sure that the virtual functions always see a consistent request for alignment. And finally, because memory resource, we're no longer a class template. This is just a regular base class. Therefore, when you're trafficking memory, we're going to be trafficking untyped memory. Void star is the type that you allocate, deallocate, and handle when you're dealing with this interface. There's also this is equal interface to say, do these 2 memory resources interoperate? Can memory allocated by one be deallocated by the other? In general, the answer to that is if they are the same object, so they have the same address. That's the default behavior here. It's customizable, but I've not yet had a need to customize that there myself. Then we have, just to complete out the facility, some standard resources you can plug in, because this is the general extension mechanism. The new delete resource is simply, it calls the new and delete operator, or operator new and operator delete. The null memory resource is that classic allocator that has no memory, so it always throws a bad alloc every time you attempt to allocate something through it, which is a bit odd, but a lot of allocators turn into a chain of allocator adapters, essentially, or resource adapters. So a null memory resource is a handy one to have at the end of the chain that says, I've exhausted all memory, give up. Or you might route it at the end with the new delete allocator that just says, okay, I'm going to fall back out to the system allocator. We also have the notion of the default resource, which is the memory resource your PMR data structures are going to use if the user does not actually specify an allocator at the time they construct the object. You can also set that, but I was just showing which ones are available. Then we have actual allocators you can use. Sorry, allocators is Bloomberg talk because that's how we do this. Resources is the standard terminology. So we've got 3 standardized memory resources. The monotonic buffer resource, which is the one I alluded to earlier. You say, here's a slab of memory, and it's really light bookkeeping that just moves a pointer every time a request comes in. if you hand memory back to say, I'm done with it, it doesn't try to reclaim it. It's not going to try and slice and dice this memory buffer. But it consumes the memory, and as long as you don't exceed it when it all goes out of scope, everything is fine and dandy. We've got the synchronized and the unsynchronized pool resource, which are the way you might manage a memory pool, which either might be shared or not between different threads. And the classic way you would gain performance is you might have an unsynchronized pool resource that delegates its memory requests down to the monotonic buffer resource. And that's how you would end up with essentially a memory pool based upon a slab of memory that is an array local in your call stack for your function. So idiomatic use of PMR, because we have these different schemes of allocators, knowing which one to call on when is something that comes with just a little bit of practice in education. But we tend to think in terms of three different allocators. You've got the system default allocator, which, as I said, will default to the new delete allocator, which is the allocator you'll get unless you say something otherwise. The object allocator is the allocator that you pass through the constructor when you initialize your object. And that will be the allocator for that object throughout its whole lifetime. And then we have global allocators, which are those that have to manage memory that's going to persist beyond the function call, and perhaps persist beyond, start before main or extend after main. So you want to make sure that they are global, stateless, they will work for the entire length of the application, but they're handling something specific rather than being the default resource. We call those global allocators. So the question becomes, if I'm writing a function, which allocator am I supposed to use for the object I construct within that function? And the general principle is, always use the default allocator unless you have a reason otherwise. And the reason otherwise is, I've got a member function, and I'm going to be storing data persistently beyond this function call. So I'm inserting into a vector, I'm going to create an element in that vector. The element that I'm going to create or transfer into that vector should be constructed with the same allocator as the vector itself. Because when you do the insert operation, that's what the vector is going to do. It's going to create an element with that allocator, and if your allocator is not the same one, you're going to have a redundant allocation as it copies the data out of the element, the object you're trying to insert, into the one that uses the correct allocator. If you've constructed your local object using the vector's allocator, it will efficiently move in. On the other hand, if you're constructing any temporary object that's not intended to go into that vector, you should not be trying to use that allocator for your data structure, even if it's a member function, because we have examples like we've already mentioned of the monotonic allocator that just consumes memory and never gives it back. If that kind of allocator has been installed in your container, or your object that's trying to be allocator aware using this facility, you don't want to be using up that memory for transient objects that happen to be local to a function call. So we do not use the object allocator for every allocation within every member function of that class, but only for allocating objects that we intend to be persistent storage beyond the end of that function call that will be maintained by that object. And so the other notion is the global allocator, which is essentially for static storage duration types where you might want to have something other than the default allocator. And the other thing that we have to mention about PMR, because this is could be key to where I'm going later on with what we're proposing to move forward. As a first step, we do not have support for allocators that need to traffic in special memory. It's a non-limitation of the system, and known to be something we need to address before we can have something that will really address the needs of a future C++ standard new allocation facility. So a quick example of using PMR to highlight some of the issues. Here I've got a monotonic resource. I'm constructing a string X with that resource. And the intent is, because the string is constructed after the resource, there can be no dangling pointers and strange memory allocation leaks and issues, because the string will be destroyed before the resource, so the lifetime of the memory that the string gets is good until the end of the lifetime of the resource. Unfortunately, something we have to be aware of, if I try to leak that memory outside of the function. So for example, by returning that string, by default, return X I would expect to call the copy constructor. I'm not passing an allocator to that copy constructor. I'd make a copy using the system default allocator and all would be good. But in practice, there's a chance for return value optimization to kick in here, which would then mean I would be literally leaking that X with a dangling reference to my monotonic resource. And when I say that there's a potential risk here, C++17 will guarantee that RVO behavior. So it's gone from beyond a potential risk that we try to protect ourselves with by saying our copy constructors our copy constructor by default will use the default allocator. This doesn't go through the copy constructor anymore. So to protect ourselves, this is the one corner we need to be aware of. If you're returning by value out of a function, something that might be consuming an allocator that is within the scope of that function, you need to force creating a temporary object that will then construct using a copy with the system default allocator that will have a storage duration that's saved to return. So it's a nasty little corner that once you're aware of it becomes second nature and not too surprising, but it's one of those speed bumps as you're coming into the system. The other key part of the PMR model, though, is what we call the scoped allocator model. And again, this is underpinning an awful lot of where I want to go with my notion of trying to add a language facility here to support allocators. The notion of the scoped allocator model says, if I am maintaining a data structure, such as a graph, a map, a list, all the objects participating in that data structure should be using the same allocator. This is how I maintain the locality. It's how I can maintain other guarantees, such as if I want to just leak all the objects because I don't know they do nothing but manage memory, there's no other hidden resources there, I can just let the memory resource itself do the whole cleanup of the data structure, and that leak is then safe. It's not a memory leak anymore, it's an object leak, but if those objects are safe, essentially it's a form of garbage collection. So this is the notion of the scoped allocator model. Every element in the object graph, everything that allocates memory in that set of objects will all use the same allocator. This is guaranteed by the way Allocator Traits will perform the construct method for you. It will sniff out and say, if my type uses a PMR allocator, I will make sure that when I construct the element in place, I will construct the element using the allocator of the container. I say so key benefit for getting the performance of the locality. It's also how we guarantee that we're not going to be having dangling references leaking objects whose lifetime extends beyond their allocator. Because if I'm in that data structure, I'm part of that, everything that is using that same allocator. And then, as the example we saw earlier, you declare the memory resource just in line before the data structure, and then the C++ object model guarantees that it's going to clean up in the right order, and there's no facility to leak beyond that, unless you invade and try and do something strange. It's correct by default. And this leads to the model that allocators therefore do not propagate. Because if I want to assign, I've got a vector of strings and I've got another string and I want to assign that string into my vector. If the assignment were to say, I'm doing a move assignment, I'm efficient, I'm going to give you my allocator to manage the memory and keep that efficient, I've now broken the guarantee that all the objects in the vector have that same allocator and know how to manage and handle that. So if I'm trying to insert something into a vector of strings where the string coming in has a different allocator, I might try to move, but the vector is going to turn that into a copy. Whereas if this were with a system that wanted to, this is what the allocator traits we were talking about earlier, you could factor say, no, I'm using a different allocator model, I will allow that to slide in. By default, all the traits default to say, we don't propagate because managing this lifetime concern has turned out to be a way to write reliable software using custom stateful allocators. Something like standard allocator that's stateless, it tends not to matter. So this is how we plug the memory resources into a C++20 container. We have standard PMR allocator, which is a simple type-based allocator that wraps the memory resources in order to work with the C++ standard containers and the allocator traits. We have, as you can see, the appropriate things we plug in to make it work with the C++ allocator traits model. We have to declare the value type, and we have to be able to construct a polymorphic allocator of one type from a polymorphic allocator of another type. So those are all just how you make the facility work. For C++20, we get to default the object type to say, it would be really nice if we wanted just to have a single instance of this class and use that consistently to allocate memory. This is much more where I'm trying to work outside the C++ container model than just as a general purpose allocator. Standard polymorphic allocator of byte means I can then use the construct, destruct, and all these other methods that automatically handle the different pointer types. So polymorphic allocator, empty angle brackets will just do the right thing and can become a new vocabulary type is the intent. And also to catch strange errors when people do try to propagate these allocators when they're not supposed to. Given the allocator trait says these don't propagate, we have deleted the assignment operator, which will just catch more errors at compile time for you. So this is the basic interface that you have in C++17. The deallocate, construct methods that you would normally specialize for a container, for an allocator. The interesting method is the polymorphic allocator select on container copy construction function, which is how we manage the case that when I'm making a copy of an object via copy construction, which allocator do I use? Naively, the default of allocator traits is to say, I'll use the same allocator as the object I'm copying from. That's not the model we need for PMR. In that case, we want to say, no, if you haven't told me which allocator to use, I want to go back to the system default allocator, which we can do. It's a facility we've added, whereas allocator traits wouldn't know what a general purpose allocator might fall back to. So this is the customization point that handles that. Finally, for C++20, in the intent we would like the polymorphic allocator to become a general purpose vocabulary type. We've added a variety of methods just for dealing with general purpose memory allocation without having to go through allocator traits. So PMR does have its limitations. The key benefit of PMR is we're trying to solve the vocabulary problem where I want interoperable APIs that do not bind into the API different allocator types. Where I've got one kind of allocator over here, one kind of allocator over there, and now I've got two different vectors that are not, I can't pass them through the same API unless I turn that API into a template, because the allocator is a compile time trait or property of that class. By using PMR with this dynamic dispatch through traditional C++ runtime polymorphism, we get to have the same type is consistent for all APIs everywhere. This does mean we're giving them support for fancy pointers because we have to have a specific return type for our virtual functions, and that's not what we support fancy pointers. That's a deliberate choice on our part, but other folks might want to look into supporting things there, where you again end up with more templates and a family of different ways of doing allocations. It's a complexity we didn't need and didn't want to get lost in. It does mean we're storing an extra pointer in every object repeatedly through the whole data structure, because every object that manages memory is now storing a pointer for its allocation. And there's again the cost of dynamic dispatch, but if you look at John Lakers' talks, you can see why that shouldn't be an issue as compilers get better and better at optimizing virtual to static dispatch when they can determine the actual final type, because everything's handled, as we say, by the lifetimes down the call chain. So what's been the Bloomberg experience with allocators? I say we provided the PMR model to the standards for C++17. So although we don't exactly use PMR, we've got our own internal progenitor that turned into PMR. We've been using it for a decade or more now. The allocators were definitely a big win on performance critical code, where we've got real low latency concerns. That this is what we want to be reaching for. And the instrumentation side has been helpful in when there's bottlenecks in the system, we can turn on instrumentation and try and find out what's happening, and is super useful when we're trying to write test drivers to make sure the code works correctly. But even though we've got a demonstrated big win here, we still have users bridling at the code complexity, which is where I come to the notion of what causes friction with the PMR allocators. Given that's such a wonderful thing for Bloomberg, what issues were we seeing? Well, the biggest problem is just parts of the language that this library allocator model cannot reach. In particular, if I've got a regular C++ style array, there's no constructors there. So I don't have anything I can plug in my allocator to say when my PMR string of my array of 42 strings is built with strings, each of those strings is just going to get the default allocator, I have no control. We say, but we have standard array. That will solve the problem for me. But standard array is, in order to pull off the tricks it uses for the syntax, an aggregate, which means, again, we can't provide constructors to take the allocators that we would need the system to take. Lambda captures lambda objects. Well, this is a class that's manufactured by the compiler. I have no control over that, and that class does not have support for custom allocators. Structured bindings have a similar issue. Default number initializers are going to provide a value if my constructor does not provide a value otherwise. And that means it's going to just pick up whatever the default value for that initializer is that doesn't get to skew the allocator that was passed to the constructor. And again, just to show that it's not just a top-level problem, if we've got something like a vector of standard array of strings, the vector wants to pass its allocator to the strings in the array. But the way it does that is it passes its allocator to the array, and the array passes it to the string, only the array will not take the allocator. Therefore, there is no path through for the vector to say all my strings are using the same allocator as my vector. So this is the friction I was starting out trying to address. But then people come to me with the complexity of the model and say allocators are too tricky to deal with because we've got all this mess with allocator propagation that is counterintuitive. People say, if I make a copy, why don't I copy the allocator? Because I'm making a copy, I copy everything. But if I've got a reference data member, I don't make a copy of that. If I'm copying a function with the vtable, I don't copy the vtable. So although it's intuitive that I'm putting this object into the system, I would expect the copy to occur. Allocators tend to live in this other part of the system that behaves slightly differently. So I say for C++20, we gave traits to give users control over the propagation strategy. And the existence of those traits tends to make this notion complicated, especially if it's provided very fine-grained traits. So now you have to manage the complexity of different notions of traits where, what does it mean, for example, if you say, okay, my type will propagate the allocators when I call swap, but not when I call move assignment. So how do I implement swap for my type now? Or I can't default to the standard swap because the standard swap is actually going to use move assignment, and that's going to now do the wrong thing. And I say the trait of the copy construction turned out to be a function call. So there's frustration and friction here just trying to manage the complexity of the system we have in C++20. So if we were to work on a new system, I would like to strip away the complexity here so that it's just much simpler to reason about what something does or doesn't do. Then the syntax overhead is relatively high. Because the model is built through using allocator traits to access the services and facilities of the allocator, your code looks a bit odd going through these traits to do everything all the time. It's not intuitively how you want to write code. When you're writing constructors for your types, you have to have the constructors that do and don't handle allocators depending upon whether I want to fall back on the default or take this new wonderful allocator that's being supplied to me. Now, by and large, for C++03, we anticipated this need. We put the allocator as the final argument, and it would then default. So we're relying on default constructors rather than overloading to handle that by and large, until we then discovered that when you start having multiple defaults, such as when you're trying to construct an unordered map that's got a number of policy parameters, and the allocator always comes last, you now need overloads for each of the reducing number of those things that can default. So we ended up going from 8 constructors to 15 constructors in that case, just to make sure that every single constructor could be called optionally with an allocator. And again, we've got the final part here is there's an inconsistent order in where does the allocator occur. There's an assumption that it will be the last argument to a constructor, because that was the model of C++03. And that turns out to be really awkward when you're trying to deal with variadic templates and things that just stream off the other parameters at the end, and how do you get the last element out of the pack. So the preferred new method is to say my allocator aware constructor will pass allocator arg and then the allocator as a tag at the front of the sequence that's much more easily sniffed out by template metaprograms and so forth from a generic code to say this is how I can instill the allocator here. And these are the sort of things that the allocator traits construct method are trying to sniff out and automate behind the scenes for you in order to make sure that when I pass a PMR allocator to an object that's using the PMR allocator, it can spot these constructors and say, okay, I now know to call the right constructor and pass the extra allocator through. But as I said, it now means you're having to write all those extra constructors. And then we've got that nasty copy constructor issue that we're dealing with the copy collision rules that I addressed earlier. But yeah, I keep banging on because this is the main risk of leaking memory out beyond the scope that we have. With the current model, there's not a whole lot we can do to help out there. If this were to move perhaps in a language-supported direction, we might have better hope of some compiler help there. So anyway, clock is just starting to help me out to see how much time I've got. So yeah, we're still doing well. So the key aspect of this talk then is to talk about what can we do to reduce that friction. That's the end of the recap, finally. So my ideal model. So this is an ambition that we're not going to achieve by the end of the talk, but it's the direction we're trying to head into, is to remove all that allocator syntax spam in the interface where we've got all these extra allocators and like pass them through constructors, and it's just an awful lot of overhead on every class author. We do want to enforce intrinsic in a compile-supported allocator model, the scoped allocator model, that a single data structure uses that same allocator throughout. I say it's turned out to be a really important thing just for writing correct code so we don't get surprises about references to memory leaking outside the data structures themselves. We believe that's an important thing that should be intrinsic in the model. The other principle is that if a type does manage dynamic memory, it should always support an allocator. Because otherwise, again, you start getting memory that's outside the model, and it's much harder to reason about lifetime to get your performance that you want it to be. So we want this to be so simple that it's not surprising that you always have allocator support for any type that would want to manage memory. So we come down to the notion that allocator aware types will then be known to the type system, because this is an important thing to be able to query about in generic code. So I'll have some kind of trait that I can query to say, is a type allocator aware using my ideal model here? And I can also query it in a portable, consistent way to say, which allocator are you using? So I'm going to coin this term allocator awareness. Lots of people have had different notions that they might want to use this term for in the past. So this is going to be my notion of what allocator aware will mean in the context where I'm going. A type is explicitly allocator aware if it says it is. So we're going to have to find some way to mark a type to say, this is allocator aware, this knows how to handle all the allocator models. And a type will be implicitly allocator aware without any user syntax or user having to write anything extra into their code if it derives from an allocator aware class, or it has data members that are allocator aware as well. So it's kind of like virtual, having a vtable, only it's virtual on members as well as bases. And at the end of the chain, you end up with this type that's explicitly allocator aware that can then trigger that all the way through the rest of the system. So why we make it implicit from data members? We could try and do something clever and just say, no, you always come from the same base class to opt in. But turns out for especially cases like arrays and aggregates, we need the behavior to be implicit, and it needs to come from the data members themselves. And trying to put extra syntax in here, especially to handle generic code, it's going back towards the more complicated model of intrusive syntax we're trying to avoid. So our ambition is shoot high, and that means this facility has to be implicit from having data members that are also allocator aware. So I say this is the two key cases that were driving me in that direction. What are the properties of an allocator aware type? An allocator aware class will obviously use a supplied allocator for all memory needs of the whole data structure. We need a consistent API to query which allocator to use. So if I'm trying to construct something that's going to go into that data structure, I need to construct my object using a compatible allocator. So I need to be able to query it out. And again, scoped allocator model, the object allocator will not change during its lifetime. Essentially the C++ 20 model where allocators never propagate ever. Why do I need this query? As I said, one, when I'm trying to make an object to go into the container, but also some operations have preconditions. I'm going to be able to move and swap efficiently if two objects use the same allocators, and therefore their memory is interoperable. One of the nice things, if I've got a vector of strings, and then all the strings in the vector all use the same allocator, by the nature of the system, I can then use any algorithm on there and know that all those operations that are moving and swapping are never going to have to worry about these objects having incompatible allocators. That's part of the constraint that we build into the system by mandating the scoped allocator model. Everything uses the same allocator. We then do get a concern with the swap operation. What happens if I have two objects of the same type, but they're being installed with different allocators? Well, the standard swap contract says that swap works. I'll just call the move assignment operator, and the move assignment operator is going to effectively make a copy using the different allocator of the other container in order to move the elements in there. This worries people though, because this is a potentially throwing operation and people like swap to not throw, and it's a linear cost now because I'm allocating new arrays or new whatever of these objects that are having to swap. So again, it's no longer the free operation. Now, that's because you moved outside the constraint that this all works really well. Stateless allocators in C++ 20 relied on this. But again, if the allocators are the same, we've not changed the contract here, or the expected contract that goes beyond the desire of the primary swap function. The alternative that the standard, to my mind, unfortunately has taken, is just to declare that it's undefined behavior. You're out of contract if you try to swap two objects with different allocators. I think that's a poor choice because ADL swap is supposed to be a primary customization point, and the primary contract for swap is a wide contract. It has no preconditions. So I'm uncomfortable with the idea that swap for containers suddenly introduces preconditions. So again, with where I'm going, I'm hoping that we don't fall down that particular route that C++ 20 has gone, but those are effective. There's a fork in the road, you've got two directions there. But that's also, again, if that is a narrow contract, there's a precondition on swap, I want to be able to verify, even if it's just through an assert, that I'm in a position I can actually call swap, so I need to be able to query the allocators of those objects. So again, my goal here is I want to simplify construction. And the way I'm going to get there is I'm simply not going to provide overloads for allocators on every constructor. We'll just assume every allocator has the option to be passed an allocator. But to do that, I'm going to invent a new syntax you can see here. I'm going to pass this extra information to any constructor or initializer, so we can work for aggregates and arrays, that just says, do your initialization using this allocator. It's effectively a hidden implicit argument or something that can be passed through to the aggregate initialization syntax. However, the language has to manage to get this allocator through to the correct initializer. So effectively, if I've got an allocator aware type, every constructor is implicitly going to be allocator aware with this potential for a hidden using allocator. If I don't using allocator, it will just use, again, the system default allocator. And for the system, we're going to plug it literally around std_PMR. We don't need to invent a whole new vocabulary to handle type-erased allocators in that sense. So this is all going to build upon PMR and the existing C++17 default allocator. So here's an example of how this might look. Given an existing C++20 type, a class object with a standard PMR string for a name, I have to declare my allocator type so the system knows that I'm using polymorphic allocator, and that plugs into making sure that it gets picked up correctly by all the current containers through Allocator Traits. All my constructors have this extra default allocator type to say you pass me optionally an allocator, which means, of course, my default constructor is now explicit because I don't want it implicitly converting from an allocator to say an allocator is an object. But you'll spot we have split up the move constructor, because the move constructor is special, that when I'm trying to move constructing is the one place I don't fall back on the default system allocator, because a move construction's purpose is genuinely to move. If I own memory, the only way I can manage out memory is if I bring the allocator with it. And constructors are special because at this point in time, I do not yet know what my allocator is. So I'm not in danger of changing my allocator if I take the allocator from the incoming argument. I'm just saying, okay, that's the one I'm going to use. But in all cases, to avoid strange lifetime issues, the general trend is always use the system default if no allocator is specified, other than for the special case of the move constructor. So with the new model, where we start being able to make things implicit using my funky using syntax, we no longer have to pass the allocator through the interface. You'll notice I'm now using std_PMR2. Probably later in the slides I'll be moving to std2. As I was working on the slides, I was in two minds about which namespace all this work should go. But this is already looking much simpler. I've lost all my funky extra allocator arguments. I can equals default my my two constructors here, and because the using is interacting with the system, I don't need this extra funky overload for the split move constructor because the system's going to handle that. I don't need my fancy type def because I'm part of the new system that isn't triggered on using type defs. And we can go a little further. We could perhaps use the default member initializer so that even the default constructor can now be defaulted. And this is your regular rule of 6, where you've got these 6 standard special member functions, and each one of them can now be defaulted, and I have full allocator-aware support, which is neat. Of course, we can go further with the rule of 0, because if they are all defaulted, I don't need to write any of them. And this then becomes your minimal example of how to write an allocator-aware object. I think you'll agree, hopefully, it looks a whole lot simpler than this version did. These are intended to be identical in terms of behavior, with the exception that when I want to create an object of my new type, rather than trying to pass the constructor through the allocator, I'm passing it through this new using res resource example. So what does this mean from the perspective of language design? How are we going to implement this notion of allocator awareness? Clearly, at construction, like we have the PMR, I'm having to store away the pointer to the memory resource. At some point in the future, we're going to want to be able to perhaps customize that API so that we don't need to pay redundant storage if we don't want it or have some extra ability to handle this. My classic example here is standard optional, where when standard optional is disengaged and doesn't have an object, I'm going to have to store the allocator in the standard optional object so that it knows which allocator to use. But when the object is holding a value, well, that value also holds the allocator. So I can optimize out the storage for that allocator if I can control and customize the API by saying, well, when this holds an object, I'll collect the allocator from the object itself, and then when I clear it again, I will effectively replace it in that same region of storage. I go back and put the allocator there. So this is certainly not something that would happen automatically through my new system. This is where you do need to step in and start taking control. But the point is, you don't need to step in and take control until you're trying to do something that is unusual and very precise. And even if we didn't do this, the system could work. I'm just now trying to optimize my use of not making my objects larger by a whole pointer when I don't need to. So it's an optimization opportunity, not a functional need. But it's still, we want, this is C++, the closer we can get to the zero cost abstraction, the happier we are. So the goal is, this is our chance to make sure that the customization opportunities are there in order to squeeze out the last of the data that we might need. And again, the implicit awareness is this whole notion that because I've got an allocator aware member, I become allocator aware. I'm not having to write anything on my classes. This is the lean syntax that just makes a feature correct and silent by default, just does the right thing, and absolutely requires a new language feature to get there, even if it's just a special new use of the using. I did look into what would happen if I were to create, like we have standard polymorphic allocator for the PMR memory resources. If I have a PMR2 allocator that is implicitly allocator aware because it's managing an allocator this way, does this make my existing standard C++ 11 containers new style allocator aware? And magically, yes it does. But as you play around with it a bit more, you find it's not perhaps the ideal way to expose that, partly because all those containers currently have interfaces that explicitly traffic in allocators rather than necessarily through the using syntax. And you're giving a lot of the simplicity we were trying to achieve. It's not clear that the shim to go that way would be worth it, but we're still looking. So the key notion of this model is what I'm calling allocator injection, which means that the allocator that you're going to use for your object, for your data structure, is specified at the time you initialize the object. That's where the injection comes in. It's not part of the type system. It's not part of it's something you either explicitly supply or you get for free. This does mean that, as again, this is largely summarizing what I've already said. We do need to put this new using syntax. It might need to go a little bit further, things like the new operator. If at the moment the model is written around doing something with allocator traits and allocator traits construct, that's where the shim goes in. But the new operator is probably another good place where you want to be using on the end to say the using that allocator goes into the constructor for the object. But I also want to pass that down to the new operator itself so that when I'm allocating, that's going to go into that construction, the same allocator gets passed to the new operator as to the constructor. So we end up with this implicit constructor argument that you will notice I've not provided a name or an access to that argument. The constructors I was showing don't actually have any extra place to pick that up because it's just implicitly provided by the system through, then you go through your base member initializers. It's again implicitly supplied all the way through. There's nothing you've got to do to forward it. In fact, you can't get in the way of forwarding that allocator. So the question then becomes, how do I get access to the allocator in my constructor if I'm not seeing it coming in from the function parameters? And the answer is, once I've called the constructor and I've gone through my base member initializer list that I have no control over the forwarding, I can then use the query API on myself to say, what is my allocator if I need it? So again, with that, the whole notion of propagating the allocator through the system becomes implicit. So early experience with this. Again, another collaboration, this time with Sean Baxter, who's been working on the Circle compiler. And I wrote this, said, meaning been working on it for like 3.5 years. This was prepared maybe 12 months ago, possibly 4.5 years now. But Sean has written his own complete front end for C++ with a goal of being able to put his own language extensions in towards it, say a post C++, an extended C++ language called Circle, which has all sorts of interesting attributes and ways to be even more meta about code than C++ is. And to do this, he's got an incredibly lean, efficient, refactorable design, so it's very easy for him to add new features into his compiler. So after seeing my talk for CPPCon a couple of years ago, he went away and implemented my using syntax. It took him about a week because his compiler is just that flexible. And he came back to us and they said, yeah, great, let's work together to see what we can do with this. His initial experiment worked really well in the existing standard library. Didn't need to go off and provide, change the API to work with this. We didn't go off write our own classes. His implementation, just on the using, doesn't have any of the other allocator injection and everything else we were talking about. Just relies on the allocator type markup from allocator traits and the existing allocator aware constructors. And using that, when he sees the using, he knows how to pass the allocator through the system in the same way that allocator traits does. And when he did this, it turned out that CTAD is the acronym we tend to use for this now, constructor template argument deduction, just fell out for free. So he's now supporting all kinds of potential allocators through the using, not just our model. So that was a real eye-opener. And it's simple said, when I construct my object using this allocator, given I haven't specified the template argument for what the allocator is, I can deduce what kind of allocator you want me to use by the actual allocator in the using. So that was really neat. And goes on towards some of the extensions that we might want to be able to introduce to our system in the future, although it's not on our immediate horizon. So it's an example of what that might look like. His logger HXX file has a logger resource that simply logs when memory is allocated and deallocated. Using a PMR list, he could therefore, my list, 1, 2, 3, using the logger, and boom, that goes off and constructs a PMR list int using the desired allocator, and we see all the logging. Now, second example, auto mylist2 equals, this looks like the same thing using the logger, but notice, what we're constructing here is the PMR list int r value. So for auto mylist, that's then going to say, I get to deduce all the way through this to say, again, I'm a list using the appropriate allocator, and it all falls out nicely even through the auto type deduction from the copy and move here, or moving the temporary for the copy utilization here. So it was an early proof of concept that the using syntax in the grammar at this point seemed to work fine. And at this point, we started saying, well, great, let's see how much further we can take this support. We started working on a project to see if we could get a sample compiler that would work in my frictionless way. So let me just hit my timer again. I turned off the screensaver on my laptop. My laptop has disagreed with me. Still got 25 to 30 minutes to go, so probably have time for a bit of Q&A when I'm done. That's good. So factory functions are one of the areas we wanted to start investigating. So what do I mean by a factory function? This is where things start to get a bit more involved, saying we're trying to plumb allocator support throughout the whole language and not just through constructors and so forth. A function that's going to return an object by value, if that object is allocator aware, we're going to want some way to provide an allocator for that return value. So classic factory function in the standard was something like make shared or standard string. So make shared, I say what type T I want my shared pointer to return, and it makes me one of those. there's no obvious place to pass an allocator in that interface. Although we have the allocate shared interface as a workaround for that, when I get to standard toString, I'm no longer in the template land. I just know what the string type is that I'm returning by value. And again, there's no overload there that's going to take an allocator. And we could start saying, well, let's overload all these with allocators. And we're going back to the problem we were trying to solve in the first place, that it's just too much mess and overhead to keep adding allocator support to every API that might want an allocator. So the notion here is, if we've got a function that is going to return by value an allocator aware type, I would like to be able to pass an allocator into that function with the using syntax. So that's our choice. But then we have the choice again of, is it implicit just every time I see a return value? Or do we want to make it explicit so I control through overloading support for with and without an allocator? And that will leave you as an open question for now. We'll get back to it later. But the key point of this is, how do we now avoid redundant allocations within the implementation of the factory function? How does the control for that function know to use the supplied allocator that's come through silently on this hidden using argument? So that was one place that we bumped down a little bit. I'm not going to give you an answer yet because those are all open questions that have some deep-seated theories going in all directions. So we just need to get more experience, consolidate, and come back when we've got the clear answer there. And I'll get to that in about 5–10 minutes' time. The other conundrum that really beat us up as we were trying to work through this set of facilities is, what should the implicit move constructor, when it's defaulted, do? As we said, with the PMR model, we split it into two. So our notion we're showing this on the screen is two overloads. We don't have this extra using alloc in any of the proposals at the moment. Option one. What should my default extended move with allocator do? We know the regular move constructor, where it doesn't see an allocator, just does member-wise move. That's fine. Option one is to say, if I call the extended move constructor, I similarly call the extended move constructor for all my bases and members. If they can take the allocator, they take the allocator. If they don't, we don't supply one. But it's relatively easy to just go through that base and member list, doing exactly the same as we would for any other constructor. And this supports all cases where I might have something like a standard toString member that can copy and move, and say something like a handle to an external resource like a lock that doesn't allocate memory. When it comes to the extended move, well, I now need to definitely move that handle, that lock. I can't end up going back to a copy constructor, so the extended move is going to have to handle that in some way, but the extended move support of the string type can still, because it knows how to copy, its extended move will probably make a copy with the correct allocator, so delegated to that extended move should work. Option one, just make sure you always support your extended move all the way down your hierarchy, and everything just works. Option two says, no, we've got a formula, we know that how to handle move with an allocator. We check if the allocators are compatible, if they can exchange memory. So the allocator of the thing I'm moving from and the allocator that's come in through the using. And if they're compatible, I can just delegate down to the regular move, which is going to just do the move from this thing that you give me, it takes the same allocator and everything just works. But if they're incompatible, I want to delegate to the copy constructor, because the copy constructor is the one that really knows how to handle making these extra copies. And if I've got a move only type, so the copy constructor is not there, that will be ill. I simply will not have an extended move constructor for this type. It will have a move constructor, but we will end up deleting the extended move, which is kind of uncomfortable. It feels wrong, and I didn't like this approach. But Josh, who's on the Q&A answering all the questions, was very, very strongly in favour of this, and he's luckily a very patient man because it took him several months to persuade me. But and again, if we do provide the ability to do a custom overload here, to say, okay, I don't want to end up with the deleted extended move, but I don't want to default to the copy. I want to have some way to provide that overload myself. That would be ideal. That might go, again, a bit beyond where we're going to get to today. Here was Josh's example that ultimately told me I had to yield and go with option 2. I've got a vector of ints, and I've got the invariant that I've got an int pointer which points to my active element in that vector. There's an invariant, therefore, on this class that d under focus points at a value that is in the vector of int. If I was to copy the vector and copy the pointer, I will end up breaking that invariant. So by default, I shouldn't be doing that. So I will delete the copy constructor just to make sure that doesn't happen by mistake. Alternatively, it was too big to hit, trying to get the slide small, I can actually just implement that constructor correctly to say, okay, I'll find the relative offset of that pointer within the vector and pick out the corresponding element in the new vector when I make the copy. So copy can be made to work correctly with an allocator. It's just a bit more work. When we come to the move, if I move and the allocator is the same, then I move the vector, I move the pointer, and the pointer is still into the same vector, so that's good. And just as I'm stood here talking about sunrise, no, that's bad, because I've now got the pointer in the vector I've moved from is pointing to the wrong thing. So, although the example is correct, what it's trying to tell me, there's a bit more work to fix this than I'd actually realized. I have to implement the move constructor properly as well. I have not done that here. My error. But in this case, if we fell down the path that the allocators were not the same, we're going to have to make a copy of that vector, and that problem has already been solved correctly by the copy constructor. So we should just delegate to the one place that has already done the work correctly, rather than risk taking in, by default, something that's going to do the wrong thing. The default should, as far as possible, never do the wrong thing. So, in the case where we've correctly implemented the copy constructor, we come down to what do we do for the move constructor, and I've shown this split into two. In my mental model, this will all be handled under the covers by the compiler. This will just be one function that simply says, I'm going to copy or move. And if I wanted to implement this in PMR models, for example, I could do that by using a delegated constructor down to, in this case, it's a factory function because it's returning the highlight object by value. That's our model to say I'm a factory function. If I were using PMR C++20 style, I would just be adding the extra allocator argument in the appropriate places to make sure it could flow through. But I end up doing the same thing. I either return I construct a return value, I'm making it temporary essentially, that will either move from the incoming argument or copy it. And that then just delegates down to the appropriate copy or move constructor in the regular fashion. So we end up concluding that Josh's option 2 really is what we have to do there. So this was all the design questions that we were going through before we could narrow it down to say, what is our next step of the evolution of this to be? We now want to come up with a new spec that, unfortunately, I didn't get to show in time for this talk. We're going to hear in a couple of weeks from now, probably. But the intent is we're now going to work on a simplified next version of this proposal that can move us forward and gain some real experience so that by the end of the year, hopefully, we can actually have a first step proposal to bring to the C++ Standards Committee that says this is how you actually can properly drill allocator support into the language. So what's the basic feature set for our first reasonable prototype? First, we're going to pass allocators to factory functions and variable initialization through the extra using argument. And those for the basic prototype will be the only place that the extra using can go. There's a bunch of other places that we might like to look at in the future, but for the initial prototype, this will be our goal: support factory functions and the variable declarations. Those are the two important cases. To make all this work, we're going to have this special allocator type that imbues allocator aware behavior on anything that contains one of these through the transitive closure of the whole class graph, or object graph in the case of an array. To keep things simple for the first iteration, it will probably be a fundamental type, kind of like null putter or something, that behaves a bit like a pointer, like a reference to a memory resource. So the copying behavior will be, on assignment will be handled in a sort of different way here. But this avoids us getting too deep into specifying how can I create a class type that customizes and says I'm using this extra special extension mechanism. We think that some kind of way of specifying classes there rather than building a fundamental type is probably the way we'll want to go for a full standard specification, because this could be extensible to things beyond allocators. But to drill in as to how can we implement something now and get clear experience with using it, the goal is probably just narrow that down to a fundamental type so the compiler can do whatever magic it needs to do, and then we can worry about interfaces later. All constructors of the allocator aware type, of an allocator aware type, because it's got one of these objects in its graph, are going to be implicitly allocator aware, with the special rule that the move constructor is split into two. So again, you're never going to see an allocator in your interface, and you have no ability to try and control an overload on that if you wanted to do something special. It's just allocator is either present or not, and it's all implicit. The detection mechanism to say what is the allocator of my object will be the allocator of implicit hidden friend function. Now, if you don't know what a hidden friend function is, it's when you have a friend function that's defined inline inside the class definition, and that shows up to argument-dependent lookup, but not to ordinary name lookup. So it minimizes your overload sets when name lookup tries to search namespaces, but it does find just the relevant overloads for your class. And the implementation of that will be either, oh, I have one of these funky fundamental types in my class, I'll return that to you directly. Otherwise, I will return allocator of my first member function, that's my first data member or base, that's allocator aware. So it just chains down the system. And in terms of factory functions, we're going to be providing only the implicit factory functions. We're not going to try to look at ways where you can supply allocators for use internally inside the factory function that might not show up in the object that's coming out. So implicit factory functions, they support a using parameter when the return type is allocator aware. That does raise the question that I'm writing generic code, and I'm now trying to call what may or may not be a factory function based upon whether or not the template parameter I'm constructing, and I don't know, is allocator aware. So could we allow passing a using to a non-allocator aware function and just ignore it? Should that be an error in all cases, or should this act a bit like const exploring templates where you support it if you can and drop it if you don't? That's one of the things we want to gain a little bit more experience with before we finalize that part of the spec. But that's one of those areas that we're going to be, while we're starting out with, an implementation that gave us experience, that's something we want to gain insight into. So, and the intent is to avoid creating all these extra allocations within the object. We want to implicitly supply the allocator to the return value. And that means detecting when the return value is declared. And it turns out there's a paper, well, we already got the guaranteed RVO of C++ 17 that gives us some insight. So if that's going to be my return value, I can implicitly pass the using that came into the using of the function call to that object, and that's therefore going to correctly RVO out. This isn't a leak because I'm using the allocator that came in through the using. We've also got paper P2025 for for guaranteed copulation for named return objects, which will expand the set of circumstances under which the compiler can infer this object under this. If you've got distinct code paths, so that no return path sees any other object that's being constructed, you can determine which of several code paths each case can guarantee the return value optimization. In those cases, those are another circumstances where we're trying to implicitly supply through a using to the factory function to the return value. So again, that's something, again, actively going to be exploring that, and it also means that we're going to be asking Sean to implement one of these language features, which will be interesting for the feedback to the C++20 committee, C++23 working group as well. With this set of features, we can then run some basic validation tests to say, these are the kinds of things with this model, I can now validate, do they work the way I expected, or am I learning new things because behavior is strange? So the intent of testing this before we start trying to nail down the next set of extensions is actually be able to implement, I'm calling it std2 string because I don't want too many nested namespaces. Whether or not this would be a new std2 is something for the committee to consider in due course. So I want to implement a fresh implementation of string, a fresh implementation of vector, and the idea is that implementing these using the new system, I should be able to compare my implementation of std2 string and vector to std vector and see that the new model just is simpler. These classes and class templates should look simpler. Have I delivered a reduction in complexity? Then we'll have std2 vector instantiated with std2 string just to make sure the allocators are all propagated correctly in the way we expect. Once we've demonstrated that our feature works to allocate memory the way we do expect, we can then start working with aggregate classes, regular arrays, and then if everything works the way I believe my model should work, you pick up the allocator awareness implicitly from the things you're constructed with, std array, std tuple, std pair. These regular standard library types should just work and be correct with the new model because there's nothing to add to make them work. And these should not have mostly extra complicated allocator interfaces that will get in the way. They have that complicated allocator interface, but they'll not pick up to figure they use it with our types because we're not specifying an allocator traits aware allocator. So those will then just look like their regular simple types and pick up our implicit allocator syntax. And finally, lambda expressions should then, I should be able to store lambda expressions in containers or arrays and so forth, and they should appropriately reflect the way the allocators for their captive members would work through. Open questions that we're still to research. After this basic prototype, these are the kinds of questions that we're deliberately putting off in order to get a prototype that gets us experience and progress. Argument passing in factory functions. If I pass by value, when I construct the temporary argument that's coming into the factory function, should that use the using allocator on the factory, or should it just be managed by the caller, or should I be able to put a using on the individual arguments? There's a wide variety of different design points there, and it's not at all clear which is the right direction to pursue, so we want to gain our experience. Explicit factory functions give us the ability to overload potentially on the using to say, okay, I might want to call this function with a using and therefore do something funky internally, or call it without, and it's more a regular function for the objects that are used inside that function that don't need, say, the transient objects. That could be similar just to passing an allocator as an argument. The reason you want to pass it through the using is the consistency that the model I'm pursuing is that allocator arguments always go through a using rather than through function parameters. That might be an ambitious overreach. We'll see. And that's part of the design question there. Similarly, overloading constructors and allocators is similar to the same question for overloading factory functions to see whether or not I really do need to be able to split out treating them with an allocator separately to not. The spot my basic model doesn't address the customization. The The intent is that allocator of being an injected friend function is a kind of going to be a customization point in the future. So we're leaning in that direction, but there's absolutely no intent to explore that at this part of the process. And I say, putting using in more places, function arguments, member initializers, constraint member initializer arguments. There's a variety of places you might want or deliberately not want to support using. So we've got the initial minimal set, and then we'll see if more places are warranted. And then I completely ducked the notion of unions and variant. We've got a bunch of ideas of how that might work, but they build quite a bit beyond what we've got here, so those are deliberately left as the next round of the exercise. And that is where I finish with, I think, about 2 minutes for Q&A. So hopefully Josh has been able to keep up with any Q&A that were coming in. If anybody's got any questions, I currently see no questions in the Q&A window. So if nothing is incoming, I'll be done. Thank you.